My name is Shamim Rashid-Sumar. I'm Senior Vice President, Codes and Standards at the National Ready Mix Concrete Association. My background is in fire protection engineering, but in addition to fire codes and standards advocacy, I oversee our advocacy efforts in structural codes as well as sustainability codes and standards. So NRMCA adopted the Architecture 2030 Challenge way back in 2012. Which has the goal, as you know, to reduce operational carbon and embodied carbon for the built environment to net zero by 2050. And last year in 2021, we reaffirmed our commitment to help the industry reduce our carbon footprint by supporting Portland Cement Association's roadmap to carbon neutrality. So the presentation here on the top 10 ways to reduce concrete's carbon footprint is one of several presentations that we provide as part of our education efforts to the architectural, engineering, and construction community, and in parallel to our codes and standards advocacy efforts. So this is our top 10 list of things that you can do to lower concrete's carbon footprint. I just have sort of a few minutes, 5-6 minutes, to give some opening remarks, so I can't go through and explain all 10 of these items, but this is the list here, and I'll try to hit 2 or 3 in the few minutes I have. So the first one is communicate carbon reduction goals, ensure good quality control and assurance, optimize concrete volume, use alternate cements, use supplementary cementitious materials, use admixtures, don't limit your ingredients, set targets for carbon footprint, sequester carbon dioxide in concrete, and then finally encourage innovation. So the ones I'll try to hit tonight with a little bit of explanation are communicate carbon reduction goals, ensure good quality control and assurance, not limiting your ingredients, and setting targets for carbon footprint. So 1, 2, 7, and 8. So number 1, communicate carbon reduction goals. This is really the most important step. And if you came to the hot topics yesterday evening, the first speaker, he really hit on this as well. One of the basic tenets of achieving a goal is to effectively communicate that goal to everyone on the team. And so for concrete, this is really especially important because there are so many parameters and criteria for concrete mixtures. And to make sure that reducing embodied carbon remains a priority, a top priority throughout a project, it has to be included in drawings and specifications that are communicated to the owner, the contractor, and product suppliers. So we have 3 basic recommendations. Collaborate during the design process. The only way you can set your carbon footprint goal is to understand the capabilities of your contractors and producers who will work on the project. So invite them in for your meetings with the design team. Understand what technologies and concrete ingredients are available locally. Just because a product isn't generally used in a market, example slag cement, it doesn't mean that you should not specify or that you should prohibit its use. So generally, a reason a product is not used is because there's no demand for it. So you need to create the demand by permitting it and encouraging its use. So the second part of communicating is to specify. So specifying in the concrete specification, state your goal at the beginning of this specification. In section 03300 of the specification, part 1, you can make it clear what level of carbon reduction you are trying to accomplish for the project and for the concrete itself. And then in the pre-bid meeting, it's important to communicate the carbon reduction goals in other ways. Most projects have pre-bid meetings, which can be opportunities to communicate carbon reduction goals for all products to all potential bidders. And then number 2 in our top 10 ways is to ensure good quality control and assurance. Concrete producers design concrete mixtures to meet the needs of the contractor in terms of workability. So we're talking flowability, pumpability, finishability, etc. And this is based on their local aggregates, and then also using sufficient quantity of cementitious materials to achieve the required compressive strength, which that required strength is usually higher than the specific compressive strength. So this over design, the difference between the actual average compressive strength and the specified compressive strength, is based on well-established statistical models described in our codes and standards for concrete. So there are well-established procedures for taking concrete samples, preparing specimens, storing them on site, transporting them to the laboratory, and then finally testing them in a compression testing machine or other apparatus. So concrete rarely tests well when testing protocols are not followed. If test results constantly show lower strength, then the only way to overcome that is to increase over design, which generally raises cementitious material content. So lowering over design means lower cementitious material content. For example, if you are going from 1200 psi to 600 psi over design, that would likely require 60 pounds less cementitious material, so potentially an 8% decrease in embodied carbon. So one way to provide some assurance that a concrete producer has good quality control is to require certifications for their manufacturing facilities, their mixer trucks, their technicians, and their plant operators. And we at NRMCA have certifications for those manufacturer qualifications. And the same can be said of installers and independent testing laboratories and their personnel. So in the quality assurance section of the concrete specification, we would recommend that you require that ACI installers are certified, concrete producers have their plants and technicians certified. So I'm going to jump now to not limiting your ingredients, which was number 7. Bear with me. And these slides, I think, will be available after, so for the ones that I didn't hit, you can catch up. All right. So back to number 7, not limiting your ingredients. So all too often, there are seemingly random limits that are placed on material ingredients in project specifications, and these limit the concrete producer's ability to meet performance criteria, let alone reduce carbon footprint. So having unnecessary limits on the water to cementitious materials ratio is one example. In most cases, requiring a maximum water to cementitious material ratio is unnecessary and it drives up cement content. There are times when that maximum ratio makes sense, mostly for cases of concrete that are exposed to freezing and thawing, but it's not necessary to call it out in the specification. Identifying the exposure class of the concrete for ACI 318 and ACI 301 is enough in our estimation. The requirements for this ratio for concrete exposed to freezing and thawing are outlined in the specification. And the same is true for air content. It's only required for concrete exposed to freezing and thawing. Air entraining decreases concrete strength. So for instance, a 10% increase in cementitious materials content for 4,000 psi air entrained concrete compared to non-air entrained concrete of the same strength would roughly translate to a 9% increase in carbon footprint. So we recommend that you not list a maximum or minimum cement content, a maximum or minimum supplementitious material content, or quantity of admixtures, and also not limit water that's used for making concrete to potable water. There is an ASTM specification for water used to make concrete. And our recommendation instead is to provide a table in your specification for concrete listing the most important performance attributes for concrete. So each project will have different values depending on the project requirements. For this example, Class 7 concrete for exterior pavements would have a water to cement ratio and an air content limit because of its exposure to freezing and thawing, which I mentioned, and that's spelled out in ACI 318 and ACI 301. And finally, concrete that will not be stressed for significant periods of time can be tested at later ages, which means higher volumes of SCMs can be used, and that can result in a lower carbon footprint. And the final one I'll go over quickly is number 8, setting targets for carbon footprint. So this strategy is for those who have some knowledge of life cycle assessment, experience with environmental product declarations, and an understanding of global warming potential for the targets to be implemented effectively. So first, we'd ask you to resist the temptation to set carbon footprint limits for individual classes of concrete. In effect, this is the same as providing prescriptive limits on materials, and it really leaves little room for the contractor and producers to innovate and meet the project performance requirements, including budget and schedule. The best approach is to use a whole building life cycle assessment to set a carbon budget for all the concrete in the building, and this is the approach that is currently being incorporated into Appendix N of ACI 318. It's still necessary to have a general idea of what the carbon footprint of each mix will be to set a carbon budget for the building. And many concrete companies have published EPDs, or environmental product declarations, for concrete, and most would be willing to publish EPDs specifically for a project. So NRMCA has published a cradle-to-gate life cycle assessment of ready-mix concrete report and industry-wide EPD for concrete. So with this information, you can conduct a life cycle assessment to determine the embodied impacts of concrete of a benchmark building using typical concrete mixes with typical amounts of SCMs, and a proposed building using concrete mixes with high volumes of fly ash and slag, for instance. And once you've calculated the carbon footprint for the proposed building, we recommend you list that target in your specification, as we've shown here on the slide. So again, this is our top 10 ways of reducing carbon footprint of concrete. Again, you can catch up on the other ones that we didn't have time to mention, but this is what we advocate in our industry. Thank you.